Hello everybody to this new webinar series. With the increasing diversity of metallic parts, the simulation of welding processes today is of increasing importance. The simulation of welding structures enables to optimize the properties and dimensions of welded parts, even when there is a big number of weld seams or weld spots. This webinar series likes to explain the application areas and potentials of solutions for structural welding simulation. This includes to give an overview of the existing possibilities as well as an introduction into particular industrial use cases, together with an insight into the software itself. My name is Ingo Hahn. I'm responsible for technology solutions at Simufact and FTI. This is an overview about the upcoming 4 weeks about what we would like to show you in our welding webinars. Today I will start with the foundations for understanding welding simulation. I will introduce you into some use cases of welding simulation, and I will present some concrete fields of application. Next week, on the 11th of August, my colleague Jeff Robertson, who is responsible for business development in Americas, and of course, he is an experienced welding engineer. He will show you how to gain benefits for welding by simulation. He will pick up some further concrete practical use cases from the perspective of an engineering service provider. The week after, on the 18th of August, Marius Gatzen, Senior Project Manager Welding Simulation, will show how it works live and in color. This will be a live demo introducing you into the functionalities of the software, showing user interfaces and how to use Simufact Welding. And on 25th of August, Pavel Kazan, Product Coordinator for the Development of Welding Simulation, will guide you through a journey through the virtual world of welding structural simulation. And this will be, for technologists or for everybody who is interested in to dive a little bit more into the technical details. So we will deepen your understanding of the diverse potential of this solution for welding processes. Welding simulation. Is it an academic tool, toy, or a serious tool for engineering? I will start with an overview about our company. Who is Hexagon Simufact? I will introduce into the simulation of welding processes and welded structures. What do we talk about in this webinar? I will sum up I will show some potential benefits. How can the simulation of welding structures help? And I will introduce into some case studies to give a closer look. Hexagon is a globally leading company in sensors, software, and autonomous solutions. We as Simufact are situated in the division Hexagon Manufacturing, Intelligence, and there in the business unit Design and Engineering, our expertise is virtual manufacturing. Simufact has 3 main product lines. Here in the middle, you see Simufact Welding. This is what we talk about, the simulation of welding structures. To the left, you see Simufact Forming. This is a simulation of all kinds of forming processes and the in-depth analysis and optimization of them. And to the right, you see Simufact Additive. This is our newest product line. This comprises the simulation of additive manufacturing processes for metallic components. Together with FTI, we form the Center of Expertise Virtual Manufacturing and Costing with 25 million euro turnover approximately and 150 employees. FTI deals with sheet forming processes and there with quick feasibility analysis and cost estimation based on virtual tests. What is our business as Simufact? We move tryout from the shop floor to the computer. That means we substitute cost and time consuming experiments, cost and time consuming physical tryout and vague analytical models by numerical simulation who take into account the whole physics And I will get back to that in a few slides to start with the benefits of that. So we will go into the simulation of welding processes and welded structures. What is it what we talk about in this webinar? Well, of course, about welding. And you all know what welding is, but let's write it down again. Welding is the most important procedure to create assemblies with a high strength and automated environment. And well, there is for me, two very important words in that. The first is the word strength. And here, a high strength, that means a high loadability of the welded structures is required. An automated environment, what does that mean? That means that we want to achieve manufacturing processes with a high robustness. So we want to have manufacturing processes which are robustly running and which make sure that we achieve a high strength of our assembled structures. That's what makes the main use case of our simulation. So, what should be evaluated when welding processes are looked at? You could first of all look into the process zone, see the melting process, the solidification, remelting, see energy inputs, melt movement, splashes, investigate the seam quality, penetration, pores, or you could look at metallurgical effects like phase transformation, hardening, softening, chemical composition. What kind of phases are there? Very important, for example, if you look at steels. But you could also look at structural effects like distortion, deformation, gaps, residual stress, or the effect of the clamping, the fixers. That means this is more looking on the layer of the components of the assembled parts. And according to this, there are three main types of welding simulation: the thermal simulation, material simulation, as well as the structural simulation. And this is where Simufact Welding is positioned. So most questions by far from industrial application deal with residual stress, deformation, or strengthening, hardening, and thus are situated here. That's by far the most relevant kind of statements we get from this. And based on this, what is typical welding challenges we are facing? Well, we have differing wall strengths, we have complex welded structures, so there's a high distortions level very often in welded assemblies due to the natural material behavior of metals. And in nearly every case, we talk of a process chain, which is important for us to optimize our structures. So instabilities in subsequent process steps due to residual stresses introduced are a problem, typically when sub-assemblies are joined. And physical testing would require the availability of parts and fixture devices at a very early stage. And this again costs a lot of money, costs time, and is in very many cases not doable. So this is exactly where we are entering and want to substitute the physical by virtual testing. What kind of processes can we simulate in Simufact? There is the most important welding processes like arc welding, laser beam welding, electron beam welding, or resistance spot welding, as well as related processes like brazing or the heat treatment, stress relief. It's very important. Many components, particularly from steel, are heat treated or also stress relieved after the welding. That's also important to simulate. And we have a quite new module included, direct energy deposition. This is a process in between welding and additive manufacturing, with at the moment still, let's say, limited industrial relevance, but all indicators show that this will be strongly improving in the future. That means it will be strongly, its importance will increase strongly in the future. So we have it already in our software to have it simulated. Which information do we need to be able to run a welding simulation? Of course, we need to to know the geometry of the intended welded structure. That's the starting point. We specify weld paths. This includes exact information regarding location and order of the weld seams, as well as the movement of welding robots. The fixation of clamping, of course, should be well defined also. It is very important to describe the heat source, because the heat input from the simulated welding process is to be considered as accurate as possible. Particularly welding structural simulation requires the specification of material properties, because we want to predict residual stress and distortion. The software provides a comprehensive database which can be broadened specifically for customer application. Having these information, the solver runs the simulation of the welding process. Afterwards, the program provides the results to the engineer for analysis. Simufact Welding has a simple and intuitive user interface to support parameter input and result evaluation. Therefore, it does not require a computation engineer or CAE specialist to use it. The user should rather have knowledge about the investigated welding processes. So, we have to talk about the potential benefits. How can the simulation of welding structures help? Because at the end of the day, we want to earn money with selling our parts of high quality, and we want to do that with as few costs as possible. So that's where the benefits should head towards. So, you have seen that picture here before. As I said, our main business is to save physical tryout. Virtual welding saves time and money. What can you do with that? You can lay out parts and welded structures, so you can early verify the layout. You can identify potential issues during layout of parts or structures. And you can check, and this is something which is very important, or it has increasing importance, and sometimes it is simply not done. To check novel designs which today would not be possible due to budget restriction. This is the layout of parts and structures. The layout of the processes themselves, the engineering, that is the classical application. To identify potential manufacturing issues, to look into the process, to understand it, and of course to optimize the process. And as already mentioned, our main focus is on distortion and stress. The most important topic during the layout of welded structures is dimensional accuracy. But which degrees of freedom do we have? Which parameters are varied and then virtually tested, or can be varied and tested by running simulations? So what can we improve in order to improve our process? I just would like to list up some of these parameters or some of these possibilities. For example, weld sequences and weld paths. You see here on the left side an example for optimizing a weld sequence. This is quite a simple structure, and you see there is 4 spot weld points, 4 spots, and the one variant, one possibility to do it is to first start here on the right side, 1, 2, and then go to the left side, 3, 4. Another possibility, another variant of this process is to do it counterclockwise, to go like that, 1, 2, 3, 4. So to have another order and another point of time when each welding spot is manufactured. And you see here that the second possibility in that case leads to a significant reduction of the distortion of the part, of the component at particular critical points. Where is it measured? On the right side, you see an example for optimizing welding paths. And I will get back to that example a little later. You see here, this is a car door. And by modifying the weld path from a continuous over stitched to another kind of weld path here, we have a strong reduction of the distortion of this car door from 100 to 85% distortion. Further potential benefit could be the effect of thermal truing. That means to bring in controlled heat, and this is done by welding equipment. So to bring in to certain very well-defined location to bring in heat at a controlled point of time in 3 different variants. And you see here that, that going from variant 1 to variant 3 strongly reduces the total displacement. That means the distortion of these sheet parts here at the end of the overall structure. You see here the total displacement in millimeters being listed. This is an application use case which is very often done. This is the to optimize clamping of fixture positioning. So we have 2 different configurations here. There's an additional clamping, so 2 different configurations for the clamping, and you see here that this affects the distortion significantly. But also the parameters of the welding process itself can be optimized. You see here for a motorcycle swing, the reduction of the distortion by changing the heat input through the weld gun, as you see here, from 4000 to 2000 watts. So direct optimization of welding parameters. Well, with structural welding simulation, the exact real dimensions of welded assemblies are predicted, often when the examined assembly is very complex or consists of many components or smaller assemblies, as you see here. The optimum order of assembling the individual components is to be developed beforehand. At the same time, it may be very effortful to provide and measure appropriate physical prototypes. Therefore, the possibility to run a virtual assembly can be very beneficial. As an example, you see here the simulated assembly process for the structural part side frame. You know how this looks, of the VW Jetta. So you see here the B pillar as it is assembled into this structure in different stages. So let me go into some case studies and have another closer look. As an example, we see here a suspension system arm, which is produced in America. The manufacturing process is shown in the following slide. On the left, you see as the very first process, a pin and a tube need to be welded to the suspension system. As a second step, a reinforcement plate needs to be put on top of the plate and need to be fixed, as you see here. And as a third step of this process, this plate needs to be welded to the suspension arm with these long seams very close to the edges. And this is where a typical manufacturing plant to do that looks like. This is from America. In America, to produce 95,000 parts per year in 3 shifts. What you see to the left, there is operators, supervising welding robots. So there is 1 operator to weld the pin and the tube, and another 2 to do the fixing and welding of the reinforcement plate. This is the process steps having been shown before. Afterwards, another 3 operators are necessary to do calibration, straightening, and machining, which is corrective work, which is nothing else than costs money. And at the end, there is 1 operator performing visual inspection and removing spatter. And the fixed invest for this manufacturing line is estimated to $240,000, which does not consider the cost for the operators. So it would be very beneficial to get rid of this corrective work, but to save a lot of money, I think, and also to release the operators from this work and let these guys do a job which is more beneficial, maybe for which is where they are, where they do their job with more benefit for the company. And this is how such a line without this corrective work could look like. The fixed invest for this would be $140,000, so 100,000 less, and the 3 operators are not longer visible here. And what could we do to get to this setup? Well, we would have to optimize the welding process so that the quality of the part, the distortions are so low, the quality is so high that the corrective work is not necessary anymore. So let's look and let's make a detailed analysis of the process in order to understand what kind of problem we produce. To weld the pin and the tube and to fix the reinforcement plate leads to a total distortion below 1 millimeter. And if I say I measure total distortion here, I measure it as the deviation of the displacement between the position here at the tip of the pin and here in the center of the cast, of the part. And well, the welding the reinforcement plate on top of the part, this leads to another more than 10 millimeters of distortion. You see it here. The deviation is visually shown. And this is definitely what we do not intend to have. So this welding process, this is where we have to focus on, and this is why we have to do some optimization steps to reduce the distortion. And that's what the customer did. This is the degrees of freedom. So what can we do? What can we vary in order to optimize the process? We can, for example, change the welding robots. Do they do one or two? Do we use one or two of them simultaneously? We can for each robot we can change the weld direction, the weld paths. We can vary the heat input, or we can do something which is called opposite pre-bowing. Let me very shortly explain what this is. If the part is expected to distort in that direction during welding, we can pre-bow the part previous to welding in the opposite direction, so that by the distortion of the welding process, the part is moved back to its designated shape. And simulated and shown here are a few variants, 4 of them I will show. We have not been allowed to show all of them, and particularly not the best ones, but we can show some interesting ones. So we can show what happens with 2 robots, and specific pre-bowing, or with only 1 robot and a slightly increased heat input and a varied pre-bowing, or another variation of the pre-bowing. So first of all, if we have the process with 2 robots, and the heat this is the heat input here, more than 3000 joule per centimeter. Then we see here how the welding process goes and the temperatures during welding evolve. And on the right side, as a result of this, we see how the distortion changes during this treatment and also the cooling down. And at the end of the day, we will end up with a distortion of slightly more than 10 millimeters relative between the tip here and the center. And this is what we have seen also before. This is not what we desire. The second variant would be to leave the welding itself unchanged, but start with some pre-bowing. Okay, the welding looks exactly the same as before, but here you see the tools which have been used to pre-bow the part, and here you see a total distortion. So we already start with a pre-bowed, a distorted value. Total distortion is always measured in positive values. So we see always positive value here. So now we see how the distortion changes during that process. And again, if we measure the distortion between here and here, we end up with a little bit improvement, slightly more than 6 millimeters, which still is maybe not where we want to go to. Okay, so we think of further variation of the process. So we shift to one robot with a slightly increased energy heat input, and we have a varied pre-bowing. If there are two figures, this means on to the left and to the right side. So again, here you see this is two robots. The welds are produced one after the other. And you see again how the temperatures change, how they evolve. And here you see the distortion of the part as a result of that. And we end up with approximately 5 millimeters, which is slightly improved, but still not where we want to head. So there's one further example I show here. This is still with one robot. So the welding process remains unchanged in comparison to the variant before, but the pre-boring is again varied. So again, the welding process and the development of distortion with the process. And we end up with 2 to 3 millimeters, which is improved, but I can tell you it's still not what the customer was desiring. So they did some further changes. But first of all, let's talk about that. Corrective work has been removed by that because the distortion is strongly changed. The pre-bowing is not typical for many manufacturing facilities. It's done sometimes, as here, in fact, really done, but it's maybe not the daily practice in many factories. But it again shows us simulation can be used to investigate variants which maybe otherwise would not be investigated. To have a look on possibilities which are maybe a little bit, which seem to be a little bit. So this can be very beneficial. And coming back to this example, they finally achieved by further optimization a distortion below 0.5 millimeters. Corrective work had been removed by 100%. So this straightening and machining was not necessary anymore. And this is also an ideal case. It is important to mention that this is not always the case. In most cases, we achieve remarkable savings by application of simulation, but of course not always the removal of defects by up to 100%. Optimizing a weld path is another nice example. So here we see the inner door laser welding of a car door as it is done at Audi. And this project has been presented together with Fraunhofer IPK. So we see here one possible welding sequence as it is used to produce such a car door with 3 different welding robots. Well, and what we see here is just one example of optimization of this seam here at the outer door, let's say, of the frame. So what you see here is the order. First of all, this weld seam is produced, then these are produced, then this is produced, and at the end of the manufacturing, the number 4 is produced. And this can be done with different kinds of seams. So we could use a continuous seam, and this leads to a high stiffness. Or they could use a stitched seam. In this example, they propose a 5 millimeter gap, and this would lead to less heat input, and we would have medium stiffness as a result of that. Or we could have, instead of that, a stitched seam with a displacement, so move every second little seam out to another location. This again leads to less heat input and a medium stiffness. and let's show to what this leads. So we have here the measured, virtually measured in the simulation, the virtually measured distortion of the car door, and this has also been validated with real measurements, with metrology equipment. So we have here two critical points, one here on the top with 100 and one here in the bottom, and this is the 100%, let's say, distortion achieved with producing this seam as a continuous seam. And when we get then from the stitched seam to this kind of seam, then we manage to reduce the distortion here in the lower section by 15%, and here in the upper region by 10%. So for the stitched seam with displacement, there's lowest distortion, and this kind of seam has another benefit. It allows for variation of the weld sequence. That means this is what we have seen before, doing this, then that, this, and then that. Of course, the order can change, but you could now have two different trajectories for one seam. Like you see here, they have started in this example with the outer seam 1, then go to the inner 2, 3, 4, and then they do this green parts at the end. This leads to reduced heat accumulation, and as you see here, it leads to another significant reduction, a very significant reduction of the distortion of the car door. So now they managed to get down to by 30% distortion here in the bottom, just by modifying the weld seam and modifying the sequence. Optimizing fixtures. Well, I mentioned it before. This is maybe one of the most important use cases done by people in the manufacturing. And here we see the example of spot welding of a wheelhouse. As you see here, so to this wheelhouse, there's a support being spot welded here at these points. And here you see the dimensions. You see here this operator. And you see here, it's quite a big part. And they have started with a configuration with 7 clamping towers. So 7 fixtures to fix the part and the support. 7 clamping towers. And well, it's quite a massive and huge arrangement. And the question is, can the clampings be simplified without a risk? So first of all, this is the simulation of the temperatures for the spot welding process. You see here some temperatures as they change. And this leads, of course, to the simulated residual stress, as well at the location of the weld spots, as well as where some fixtures are. And of course, this leads to a total distortion, to a distortion of the part. And our main aim is the main quality, let's say, objective is to keep this distortion low. And at the same time, reduce the number of fixtures. So they managed, by doing several simulations and positioning the clamps, they managed to reduce from 7 to 4 clamping towers, so to strongly reduce the complexity, and at the same time to reduce the distortion by 70%. So besides strongly reduced distortion, they achieved reduced residual stress. This can be very beneficial for subsequent process steps, but also a reduced number of clamp towers, which leads to less monitoring of sensors and machines, to a more simple working logic, since now not 7 fixtures have to be handled, but only 4. This can lead to faster manufacturing, more throughput, and an improved utilization of existing machine equipment, like robots, turntables, external axes. And of course, it's clear that such a strong reduction of equipment strongly reduces the investment. So after these use cases, I like to summarize. The simulation of welding structures enables to optimize products and processes in close collaboration, to get rid of expensive and inefficient shop floor tryout, since this is now moved into the computer, to increase product quality, increase dimensional stability, very, very important topic, and so achieve remarkable cost savings in short time and reduce time to market for welded products. So to give an answer to the question which I posed in the beginning, is it just an academic toy or is it a serious engineering tool? I think a tool which performs these tasks, this is a serious engineering tool. Of course it is. Here you see my contact data. We are very happy to channel your questions or to go more into detail with you. Feel free to contact me. Thank you very much for attending.